Hello and welcome back. Today we'll be doing question 1 from the 2018 step 2. Question 1. Show that if k is a root of the quartic equation x to the 4 plus ax to the 3 plus bx squared plus ax plus 1 is equal to 0, then k to the negative 1 is a root. You are now given that a and b in star are both real and are such that the roots are all real. Part 1. Write down all the values of a and b for which star has only one distinct root. Part 2. Given that star has exactly 3 distinct roots, show that either b is equal to 2a take away 2, or b is equal to negative 2a subtract 2. Part 3. Solve star in the case b is equal to 2a take away 2, giving your solutions in terms of a. Given that a and b are both real and that the roots of star are all real, find necessary and sufficient conditions in terms of a and b for star to have exactly 3 distinct real roots. Pause the video to have a think, and once you're ready, restart to see if you were correct. Let's get started. Firstly, we'll set x to be equal to k to the negative 1, and we'll put this into the equation, and we'll get an expression, k to the negative 4 plus ak to the negative 3 plus bk to the negative 2 plus ak to the negative 1 plus 1, and this is equal to 0. We can then multiply both sides by k to the 4, and the left-hand side becomes the original expression, and the right-hand side becomes 0. This means that if k is indeed a root, then k to the negative 1 must also be a root. Now we'll move on to part 1. Firstly, we'll start with our root being alpha. We therefore have x minus alpha all to the 4 is equal to 0, and expanding out, we have that x to the 4 take 4x cubed alpha plus 6x squared alpha squared take 4x alpha cubed plus 1 is equal to 0. We can now compare and equate coefficients, namely negative 4 alpha must be equal to negative 4 alpha cubed, and therefore alpha is equal to alpha cubed, and therefore they are equal to 0 and plus minus 1, meaning that alpha must be equal to plus minus 1. This is because if we had 0 being a root, we would need to have the reciprocal of 0 being a root, but that does not exist. Therefore, we have that alpha is equal to plus minus 1, a is equal to minus plus 4, and b is equal to 6 in both cases. Therefore, the pair AB can be equal to 4, 6 or negative 4, 6. Now, let's move on to part 2. In this case, we have 3 distinct roots, and therefore we have roots alpha, which appears twice, k and k to the negative 1. Looking at the constant term, we can see that if we multiply all of our roots together, we should get 1. And since k multiplied by k to the negative 1 is also 1, we require that alpha is equal to plus minus 1. We can now consider the cases where x is equal to plus minus 1. In the case x is equal to 1, we have that 1 plus a plus b plus a plus 1 is equal to 0, and therefore b is equal to negative 2a take away 2. In the case where x is equal to negative 1, we have, similarly, that b is 2a minus 2. We can now move on to part 3. Firstly, we are given that b is equal to 2a take away 2, and this corresponds to the case where alpha is equal to negative 1. We'll firstly start by replacing b in the original quartic expression with a minus 2. With 2a minus 2, and then we will factorize out x plus 1 all squared to give the remaining x squared plus a minus 2x plus 1. And we will equate this quadratic factor to x squared plus kx plus 1, where k is equal to a minus 2. Solving this, we have that the other two roots are negative k plus minus the square root of k squared take 4 all over 2, and we can replace k with a minus 2 to get that the other two roots are 2 take a plus or minus the square root of a minus 2 all squared take 4 all over 2. Now we need to find necessary and sufficient conditions. Firstly, from the expression for our other roots above, we need that a take away 2 all squared is greater than 4. And we can rearrange this to give a squared is greater than 4a, which is equal to 2b plus 4. In the case that b is equal to negative 2a take away 2, we have a similar case where a squared is greater than negative 4a, and this is still equal to 2b plus 4. We will also note that in both cases the non-repeated roots are not plus minus 1. Therefore, we can say that b is equal to plus minus 2a minus 2, and therefore the resulting equivalent expression b plus 2 all squared is equal to 4a squared, and a squared is greater than 2b plus 4 are necessary and sufficient for 3 distinct roots. If you liked our video, please like and subscribe, and we'll see you next time for some more fun maths problems. Thanks for watching, and goodbye.